Hello everybody, I am Fabricio Rodriguez from the University of Campinas, Brazil, and I'm going to present our work towards low latency industrial robot control in programmable data planes. So this is the agenda for this presentation. I'm going to start with an introduction. I'm going to continue with some background, a system overview, our experimental evaluation, and finally our conclusions and the future works. So the introduction. So nowadays, industrial robots are more intelligent than their predecessors decades ago. It can be faster and more accurate than the human workers. They can calculate their own trajectories from one point to other point, and they can have external sensors like cameras, motion sensors, temperature sensors, and much more. With these kinds of sensors, the robot can detect unexpected obstacles or even humans. With this, it can avoid collisions, damage in the system, or human injuries. The robots also have a direct link with the controller that is going to continue monitoring the behavior. With the new technologies, new trends like Industry 4.0 started, also being supported by the evolution of SDN and NFV. These solutions are also improved the operational management, and they have added a direct link to centralized solutions or an offloaded solutions. But with these offloaded solutions, we have some limitations like the packet loss, the congested links, and the variation in delays. And this can affect the behavior of the environment. Also, the 5G improved the network capacity and added an ultra-low latency support. But due to the undeterministic stability of the wireless connection, we still have some problems with the latency for critical applications. With the SDN and NFV, we also have the capability of programmable networks. With these programmable networks, we can add a new layer of programmability, having in-network solutions for the applications. In a traditional scenario, we are going to have the robot connected with a direct link to the controller. When we offload this controller to the cloud, what we are going to have is a robot, a network device, and the controller in the other side. In a cloud solution, the robot is going to send messages to the network device, and the network device is going to forward this information to the controller. If any action from the controller is necessary, the controller is going to send back a message to the robot. In our approach, in this work, we are going to present an in-network solution for this communication. So when the robot sends a message to the network device is going to process this message and is going to perform an action directly to the robot. For example, if there is a threshold violation that is detected by the network device is going to send back a message to the robot, for instance, an emergency stop, and the robot is going to perform that action. The network device also can send a copy of the original message from the robot to the controller just to have it in register. The background. From our implementation in the side of the robot, we are going to use the Universal Robot Simulation. The URSim is a virtual representation of a real robot arm. This simulator can work as a client and can be connected to an external controller. It uses TCP sockets for the connection, and it basically has three types of movements: the joint position, the linear, and the circular blends movement. For our implementation, we are going to use the joint position movement. And basically, this is the structure of the messages that the robot is going to be sending to the controller as the current position. In the data plane part, we are going to use P4 as a solution for the language to be implemented in the data plane. P4 gives us a solution as a high-level abstraction and target-independent implementations. Basically, a P4 program, it has a parser, a match action tables, and a deparser. One advantage of the P4 is that in hardware, it can run at wire speed. In the robot controller side, we can have different implementations, like a physical device or a programmed script. For our implementation, we are going to use a script that is going to represent the controller. The controller is going to set the positions and actions in the robot, and is going to have the TCP session with the robot for all the communication. Let's go to the system overview. In a traditional scenario, without in-network control, as I mentioned before, we are going to have the robot, the router, and the controller. For instance, if the robot sends its current position to the router is going to forward that message to the controller. If there is any action, for example, an emergency stop message that the controller needs to send to the robot, the controller is going to send back a message to the router, and the router is going to forward that message to the robot. In the case of an in-network P4 based implementation, we also have the robot, we have a P4 router, and we have the controller in the other side. So when the robot sends its current position to the router is going to process that message. As a first step, he's going to forward the original message to the controller, and if the controller has some action with this information, he's going to send back an action to the router. But the important part here is that when the P4 router receives the original message, the number 1, with the current position, the P4 router is going to process that message, and if there is any action, he's going to send back a direct message to the robot with the desired information. And how all of these work inside the P4 code. So inside the code, we are going to have the header, the match table, and the actions. In the header part, we are going to define the exact structure of the current position messages that the robot is sending to the controller. For this example, we are going to match just one of the joint position messages, and it's going to be stored here in the payload. With this value, we are going to match with a predefined threshold that is going to be in the table, for instance, this value. And if there is a match, an action is going to be applied. What is going to be this action? This action is going to be to generate a message with this information, with this data, to send back to the robot to have an emergency stop. One of the issues that we have when we are generating message from the P4 to the robot is that we are in a TCP session, so we need to sync the sequence and the ACK numbers. In our TCP approach, when we have a match inside the P4, we are going to calculate the sequence and the ACK value, and we are going to send that values in the message to the robot. We are going to forward the original message from the robot to the controller, and the controller is going to generate the same values that we already calculated from the P4. In this case, this message is going to be discarded in the P4 because we already sent that information back to the robot. In this way, we are going to have all the values of the sequence and the ACK number synchronized. With this in-network approach, we can have different use cases and scenarios. One of these can involve more than one robot. For instance, in this scenario, we have two robots. These two robots are going to send their current position to the P4 router. And the P4 router is going to match the values of these current positions. And if they reach a predefined threshold or a predefined scenario, the P4 router can directly send back messages to the robots to synchronize or to generate some actions directly in the robots without the intervention of the controller. Our experimental evaluation. For the experimental evaluation scenario, what we are going to have is a robot sending its current position to the controller. The robot is going to start a movement from a predefined position, and then the P4 is going to have a threshold. So when the robot reaches that threshold, the P4 is going to send back a message directly to the robot. We are going to compare this scenario with a scenario without the P4. So the second scenario is going to be the robot starting a movement from the same predefined position, but now the threshold is going to be defined in the controller. So in this case, the controller is going to send an emergency stop to the robot. But this controller is going to have different values of delay between the network device and the controller. And we are going to compare how this delay can affect the final position of the robot if we need to stop the robot movement. So these are the results that we have with the simulation. The first values that are marked in red are the response when we have the P4 router sending back the emergency stop to the robot. So as we can see, we don't have any error in the position from the position that it needs to stop the robot and the position where the robot actually stopped. But in the other cases, when we start adding more delay and when we start changing the steps are how often the robot is going to send the current position to the controller, we are going to have some error between the position where the arm needs to stop and where it actually stopped. So we can see that that delay can impact in this scenario, and we can reduce all that delay, all that impact if we use the in-network implementation using a P4 approach. Our conclusions and future work. With our work, we were able to offload some basic controller functions to a network device. We were able to manipulate the content of the messages inside a TCP session, being able to send directly messages from the P4 device to the robot. We also analyzed the impact of the delay in the different connections. Programmable data plane in delay critical scenarios open up new opportunities for a different range of applications, like multiple robot synchronizations. We are also working now in a testbed using a real P4 hardware Atofino device and a real robot arm. And all of this opens new opportunities in different range of applications, not just robot. It can open opportunities in industry 4.0, automation, real-time control, synchronization, also drones. Thank you And now I am open for questions.